Okay, here we go. Okay, so last time we were talking about the fundamental theorem of calculus, right? I mean, so I'd presented Green's theorem, and there was a variation of Green's theorem, and one of the ideas that I'd been pushing is this idea that, hey, even though you detect circulation on the boundary, you detect flux on the boundary, right? That's how you compute it. I claim that's not really where it is. It's actually coming from the interior. It's an accumulating quantity. It's spread out over the interior. And I know it doesn't look like that, but, it is. Right? And it's a little bit hard to swallow. And that's why I like this discussion here about the fundamental theorem of calculus. Not that y'all don't already understand the fundamental theorem of calculus. Of course you do. Right? But the big idea is that, this seemingly ridiculous claim that I'm making about how circulation accumulates throughout the interior and flux accumulates throughout the interior, we see that already with the fundamental theorem of calculus. Right? So change, is an integral. It's an added up, right? It's we're looking at changes that happen in the interior, and it's just downright. I don't want to say obvious, but maybe a little kind of. It's very satisfying anyway to point out that change, this also an accumulating quantity. Yeah, we detect it, we compute it, however you want to say it, on the boundary. But does that mean that change actually happens on the boundary? No, you measure it on the boundary. Where does the change actually happen? Well, we have a lot of familiarity with looking at functions and talking about where and how they change. That's where it changes. Right? It's perfectly clear. Watch it change. Whoop, it just jumps up. Here, right? These are the values of x. They're conspicuously in the interior. That's where it actually happened. Change is measured on the boundary, right? But it happens in the interior. So the hope is that you can use this example and the analogy between this and Green's theorem, this and the 2D divergence theorem, to help you digest these analogous assertions that I made. I claim circulation actually happens in the interior. Again, you measure it on the boundary, but it's actually happening in the interior. I cite this as a for example. Okay. Furthermore, not only does the derivative, right, my integrand of my new integral, the interior integral, you might call it, not only does that tell you where this quantity change, right, is actually happening, it also tells you how much change is happening there. And so you look down at this example. This is where we ended last time. Sure, there's a certain amount of change that happens for that function between 0 and 3. The function increases by 9, so there's a change of 9. Yeah, sure, fine. Okay, where is there more of it? Is there more change happening here at 2, or is there more change happening here at 1? Well, the integrand here, right? This integrand, f prime, that's what resolves the question. F prime, the density, the change density, tells you that by looking at f prime, which is 2x, tells you, I'm just going to get my colors straight here, that at this point where x equals 1, there's, not so much change density. But by comparison, this point here where x is equal to 2, there is clearly more change density. Right? Change density is higher. That's the indication that, yeah, sure, there's a total amount of change. More of that change is happening in this vicinity compared to less of that change is happening in this vicinity. So, and then we ran out of time. I couldn't finish the analogy. The same thing works with our other densities in our other theorems. So, likewise, Green's operator tells you where circulation is happening and how much circulation is happening there. So, for example, let's look at this vector field right here. Now, this is a manufactured vector field. It's not going to be particularly convenient for me to write down a formula for it, but the idea is that the vector field is constant up there. You see all those arrows have the same magnitude, same. It's all the same up there. And then it's likewise all the same kind of down here, if you will. Just bigger. But all of these are, it's constant in this area as well. But then kind of slowly increasing in this gray region. Kind of slowly increasing as you go down through this gray region. All right, so that vector field. Let's ask, and looking at circulation. Now again, we measure circulation on the boundary. Sure, right, fine. But we know the circulation's happening in the interior. Where in the interior is the circulation happening? Okay, well let's kind of think it through. Looking at, and again, y'all know when we're talking about circulation, I like to think in terms of fluids. Let's imagine this vector field representing a fluid. Let's imagine, for example, there's a little stream of water moving to the right, yeah, and we've got a little leaf right there. What is that leaf going to do as it's dropped in the water at that location? Well, it's going to start moving that way, of course. But is it going to have any rotating? Is it going to be spinning at all? And I pose no. It's being pushed the same on the one side as it is on the other side. This leaf is just going to kind of float on down the river and keep its orientation as it is. By comparison, though, if you put a leaf in there, it's being pushed harder on the south side, pushing it counterclockwise. It's being pushed less hard on the sort of the north side, pushing it clockwise. So yeah, there's opposing forces, but it's being pushed harder on the side that's pushing it counterclockwise. So what's going to happen to this leaf? It's going to rotate as it floats downstream, right? So this leaf would be doing this move where it's like this, and as it floats downstream, it kind of turns. And I feel like, I don't know, you might even be able to relate to that. You might have actually seen a leaf in a little creek and watched it kind of go down, and it doesn't necessarily keep its orientation. It'll kind of twist and spin around. And it's telling you it's telling you Green's operator on that fluid flow. Okay. All right. So, all together then, let's see here. This is how you measure circulation, but where did the circulation actually happen? Well, the circulation actually happened in here where the leaves are rotating. That's where the circulation comes from that you detected on the boundary. That's where it really is. Everybody on board? Feel free. Questions? Anybody? Okay. All right. Likewise with flux. Same deal. Now, so flux is a little bit of a different, circumstance. We're not looking at the fluid flowing around the curve, along the curve. We're looking at fluid flowing outward through the curve. Right? So I put these little purple arrows here to indicate which is the positive direction for the flux. So again, that's how you measure flux. You look on the boundary, and we've got formulas for how to, compute that. But is that where the flux actually comes from, right? How could it be that there's flux through that boundary? But what do I credit with the creation of that boundary flux? And, well, it's not anything having to do with what's happening over here. Right? Now, the vector field is huge over here, relatively speaking anyway, so this is where the field is the largest, but it's also constant. Right? And if I were to look at some little region over here, for example, if I were to look at some little region like this, yeah, sure, there's fluid going in, but then there's also fluid going out, and it's in the same amounts, right? There's the field strength is the same going in on the left side as it is going out on the right side. So this is just, there may be a certain amount of fluid in there, but it's not expanding out of this region. It's not disappearing into this region. It's just fluid in, fluid out. In some sense, nothing's happening. And likewise over here, just less. Right? There's less going in, there's less going out. Same amounts, right? And inward cancels outward, and there's no flux. Right? So there's no flux happening in that green region there, and there is no flux coming from this blue region here. Where is the flux actually coming from? Well, the flux is actually coming from this part here. Right? That's where the flux is. That's where the flux comes from. Think about, what's the story of what's happening at some little region inside of this, yellow area. There's let me draw a little region here. Let's look at this little region like that. Well, there's a little bit of inward flux, but there is a lot of outward flux, right? There's definitely more out than going in. So grand total in this little region here, there's a positive amount of flux, right? This is for example of where this purple flux that we measure on the boundary is actually coming from. And again, this would be evidenced by divergence. The divergence in this region, positive. The divergence let me get rid of my junk here. The divergence over here, 0. Appropriate to the fact there's no flux happening over there. None of the flux that we measure on the boundary is coming from over there. And likewise, there's no divergence over here either. Okay. And you can quantify this. All right. So let's, again, sort of compare some points. So in the same way that in this example, I used change density, aka the derivative, right, to decide between these two values, 1 and 2, right, these 2 points in the domain over here, where is the change happening more and where is the change happening less? When you look at the value of the derivative. Bigger derivative, more change is happening there, right? And again, a very familiar geometric picture. It's very satisfying because y'all been looking at graphs and derivatives and slopes for a long time now. Right? So, the change density tells you where the change is happening more versus less. So likewise, circulation density, Green's operator, is going to help you arbitrate between the two given points here. Right? We've got this 3, 3 point right there, and we've got this 2, 4 point right there. Circulation density is going to tell you where more of that circulation is coming from. And now, of course, you can see that the winner here is this point where circulation density is greater. And so there's more circulation coming from that point than there is coming from that point. Just don't even need a picture. Green's operator tells you for you. Everybody happy with that? Okay. Excuse me. And then likewise with looking at these same 2 points now, if I want to know where, if I were computing flux, where is most of the flux coming from? Is there more between these 2 points? Which one is a greater origin, a greater source of flux? Okay, well, we're going to look at flux density, aka divergence, and you look at compute the divergence at these 2 points, and it seems that this one is the one where it's greater, right? And this point, 17, this value 17 indicates a greater flux density. So more of the flux is coming from 3, 3. Yeah, so you might say that this gives you some sort of geometric intuition for what the vector field kind of looks like. Not that this is going to help us draw the picture exactly, but this point 2, 4 is more circulation-y and less fluxy, and this point 3, 3 is more fluxy and less circulation-y. That makes sense to everybody? So, very loosely speaking, of course. All right. Okay, So now that finishes 6.2. I know that I already put 6.2 on the lecture schedule for Friday because we had already finished by Friday all of what you were going to actually need in order to be able to do the homework exercises, which is what we were using the lecture schedule for. So I didn't want to delay anyone from starting on the homework exercises for 6.2. You already had what you needed as of Friday. But anyway, now we are officially done with all of 6.2. Moving on then to 6.3. We're going to start with a new theorem. First cat out of the bag, new theorem. It's called the fundamental theorem of line integrals. I like to point out that if you just look at the name of this theorem, you could almost guess what the theorem says just by the name. So, fundamental theorem, okay, that makes you think fundamental theorem of calculus, right? Fundamental theorem of calculus is about integrals. Oh, this is a fundamental theorem of line integrals. So, being a fundamental theorem of line integrals, maybe it's about evaluating line integrals, would seem like a reasonable guess, right? Now, what kind of a derivative would we expect for this to need to be involved with? This integrand here. Now, if this were the fundamental theorem of calculus, this would be the derivative, the single variable derivative of whatever the function on the right was. Well, but this is a vector field, and we're talking about multivariable functions. What plays the role of derivatives in multivariable, real-valued multivariable functions? And that is gradient. Right, so it'd be a reasonable guess anyway to guess that the vector field here needs to be a gradient, and this function over here that I like to call the antigradient. Right? I think it's reasonable terminology. That antigradient is what you evaluate with again, I mean, seems like a rip-off from single variable calculus. Right? So, anyway, this plausible guess of a theorem is in fact exactly right. If you're doing a line integral of a gradient, then that's f of b minus f of a, where f is the anti-gradient. What do you think? Does that seem plausible? Any questions so far? We got examples and discussions and motivations coming up. Okay. All right. So I'm going to show you an example in just a bit, but I want to talk about why this theorem is true. The quickest way to demonstrate this result is not the point of view that I want to give y'all. I want to develop intuition, and this isn't really a course about rigor so much. So I want to fit this in with the point of view that we're already taking on accumulations and densities, right? So far we've got Green's theorem, and we've got the two-dimensional divergence theorem sort of twist on Green's theorem, and we've got the fundamental theorem of calculus. All of these theorems, 3 theorems so far that we've seen that are basically, we observe that we've got an accumulating quantity, we rewrite it as a kind of an integral, and then we observe that the accumulating quantity, there's an associated density, and you write down the theorem. Right? So all 3 of the theorems we've done so far fit that form. So same here. So change is the accumulating quantity in question here. This sort of f of the endpoint minus f of the starting point. I claim that change is an accumulating quantity over curves. So let me explain why that's true. So specifically, my assertion is that if I look at how much the function changes from there to there, that I can view that as a sum of how much did the function change from there to there, and how much did the function change from there to there. Right? So, in other words, the change that I associate to this, the change that I associate to that, between the 2 of them, you add them up, and you get the change that we associate to the whole. Okay. So that's what it would mean to accumulate. And this is easily confirmed. Let's look at this first sort of half of the curve, if you will. Keep in mind our formula for change. We have a positive value of the function at the end point, right? And then note a minus value of the function at the starting point. Right, so in the general formula that I have here, we're going from Q to R. So this is f of the endpoint minus f of the starting point. All right, now same deal for the second piece of curve. Oh, and that is, of course, this right there, that term right there. So now let's look at the second piece of curve. And same deal, positive value of the function at the endpoint, negative value of the function at the starting point, and that gives us that expression right there. So notice that that and that cancel, right? F of x1, positive here, negative there, and they cancel. Geometrically, you might see this as this point x1 appears twice. It appears once with a positive sign as the end point of the green curve, and then here with a minus sign as the start point of the blue curve. So it appears twice with opposite signs and therefore cancels. Everybody with me? So I feel obligated to point out, very analogous to what we saw with like Green's theorem, right? If you think about Green's theorem, when we chopped up a two-dimensional region with Green's theorem, we were creating interior edges along which we found ourselves going along the same edge with opposite orientations, and they canceled. Here, we're not chopping up a two-dimensional region, we're chopping up a one-dimensional curve. So when you chop it, you get one-dimensional points, which we're seeing twice with opposite signs. And again, they cancel. It's morally equivalent, right? It's almost exactly the same thing. Just, dimensionally different, of course, but highly analogous. Everybody okay? All right. Okay, so change is an accumulating quantity. Just to make it a little bit more visceral, I like to make this observation here. And think about how much your altitude changes as you drive along a mountain road, right? The amount of altitude that you gain in the first 10 minutes, the amount of altitude that you gain in the second 10 minutes, if you add those up, that gives you the amount of altitude that you gain in the first 20 minutes. Right? It's just, altitude just keeps accumulating. Okay. All right. Okay, so how much does a function change as I move like that, from a start point to an end point when I displace by some vector amount dx? And I'm going to recall this old formula from chapter 2, right? That input change and output change are related by the gradient, right? So the input change here, how much we move in the domain, is the dx vector. The output change, how much did f change? F of b minus f of a, right, is what I'm abbreviating with delta here. And the gradient is the relationship. Does everybody remember this from chapter 2? I hope. Okay. All right. And then, of course, I'm going to rewrite dx as t times ds. So that I can move parentheses around a little bit. Now let's look at this formula here. What I like about this version of it is that now I can talk about change per unit size, because ds is a size, right? ds says how big is that piece of curve. ds is a scalar. It's just about size. It's got nothing to do with direction. And so we can talk about change per unit size, and if we were going to have a notion of a change density, right, that would be it. This is the thing that you multiply by size to get quantity, or accumulating quantity, right? So the thing that you multiply by size to get quantity is the thing that you could call quantity per unit size, aka change density. Everybody okay? Okay, so I'm going to skip this stuff about orientation just momentarily. I'll come back to that in a second. But with this alone, we're already ready to write down the theorem, and that is, here it is. We've already observed that change is an accumulating quantity, so I can take my curve, chop it up into little pieces. Total change is the sum of all these little bitty pieces of change that you have along the way. This is just accumulation. And then writing this here on each little piece, change is change density times size, ds. And we've got ourselves a theorem now just for aesthetics. Maybe we'll recompact TDS back down to dx. But having done so, notice f of b minus f of a is integral of the gradient. That is our fundamental theorem of line integrals at the top of the page. And so we've proved our result. Everybody on board? Big takeaway here is notice that it's structurally, this argument here that we've done is structurally equivalent, morally structurally equivalent to Green's theorem. Accumulating quantity, corresponding notion of density, theorem. Okay, so let me come back up here now to this. Let's talk about this oriented density business. This is nothing to get too concerned about. It's just a kind of a different way of thinking about density. Before I get into this, I want to remind you we've already kind of broadened pretty significantly our idea of what density means. So when you came into this class, you may have thought of density in a very narrow, specific way, like I did at some point in the past, right? Which was, it's mass per unit volume, right? That's what they told me in high school. That's what density is mass per unit volume, right? So we've broadened that in two ways. First of all, we don't require it to be mass specifically anymore. If it's mass, then yeah, you'd call that mass density. But hey, maybe we're not looking at mass. Maybe we're counting population, right? Or maybe we have some other quantity that we're interested in. And so why don't we just say quantity as a whole, right? Whatever the quantity is. And then in the denominator, volume, well, it makes sense to talk about quantity per unit volume if you're talking about a three-dimensional region. But if you have something that's distributed over an area, or if you have something that's distributed over a curve, it doesn't make sense to talk about quantity per unit volume. So we generalize to quantity per unit size. Okay, so we've seen all that stuff before. What I want to do is generalize a little bit further and point out that while size does, in some way help us get a hold of what we've got here in terms of how big is this little piece of curve, notice that there's another perfectly good equation here relating what you might call the size to the quantity. It's just that the way this is written, I'm thinking of what I might call an oriented size. Right, so dx tells you by its magnitude the actual size, but by its direction it's telling you more information about that little piece of curve. And so I'm going to call that oriented size. It's just saying it's a vector, right? But I'm going to call it oriented size because I still want to think of it as playing a role kind of like size. So if you think of not quantity per unit scalar size, but quantity per unit oriented size, right? What's the relationship between oriented size and quantity? Well, that relationship is this thing here. And since this thing here, the gradient, relates quantity to oriented size, I call it an oriented density. Right? The orientation, the direction, that's part of what the gradient vector is, combines with the direction, that's part of what the dx vector is. And between the two of those, that in the form of the dot product, accounts for how much the function is changing in the direction you're actually going and how much it's not. Okay, so it's just semantics and a little bit of open-mindedness as to what words are allowed to mean, right? So anyway, this is the new idea that I want to get across, is the idea of an oriented density. And so that allows us to see the density even when we write the theorem in the more usual way, right? This is kind of the more convenient way to write the theorem. And where's the density? Well, the oriented density. We're talking about the quantity of change here. So the oriented change density is that integrand right there. How are we doing? Is everybody on board? Okay. All right. FYI, we don't have any particular upshot to this point right here. This is more of a sort of a conceptual point combined with there actually is going to be an upshot when we get into chapter 7, where there's going to be a different kind of an oriented density that we're really going to need to have some intuition for. So this is kind of laying groundwork for some future chapter 7 stuff. Okay. All right. So, theorem, discussion of why it's true, restatement and semantics. And now let's see an example. Compute a line integral. Compute a line integral. Got a vector field given, got a curve given. Real quick, let me observe. Notice nothing in the statement of the question here says anything about using the fundamental theorem of line integrals. That's the way it is. That's the way this turns out. Problems don't usually announce the solution within them, right? So we just need to compute a line integral. So how are you going to compute this line integral? Well, you could plug and chug, right? You got a parameterization sitting there, right there looking at you. You could pull back through the parameterization and crank it out. Let's not do that here. Not that we couldn't. We could, but look for better options. Hey, how about Green's theorem? Green's theorem is a tool for computing line integrals, isn't it? That's our existing cool tool for computing line integrals. And that'd be worth a shot, but don't forget, Green's theorem comes with a catch. And I'm going to scroll back so I can remind you of that. Let's see, where is it? Here we go, Green's theorem. The catch with Green's theorem, if you're going to compute a line integral, it says right here what the catch is. The catch is, can't be just any line integral. You need for your domain to be a boundary. It's got to be a closed curve. Otherwise, not only can you not use Green's theorem, there is no Green's theorem. There is no anti-boundary over which to even talk about a double integral, much less entertain the question of whether it's equal to what you want. There just is no such thing, right? So that's the big catch with Green's theorem. And sadly, you'll notice here, if I can get back, almost there. Here we go. You notice this curve doesn't go all the way around, so this curve is not a boundary. Green's theorem does not apply. There is no Green's theorem as far as this question is concerned. Everybody with me? All right. Let's try our new theorem, the fundamental theorem of line integrals. Keep in mind there is a catch here as well. And again, right here in the statement of the theorem, you can't just compute any old line integral. It says right here that your integrand has to be a gradient. By the way, a little lingo, aka conservative. And I'll talk more about that later. But that's just a little bit of lingo. It's got to be conservative. And again, this is not some sort of formality or regularity point. It has to be a gradient of something, because that something is the function that I'll be plugging into at the end. So if my integrand is not a gradient, said differently, if there is no anti-gradient, then there is no f, there's no formula to plug into. There's just nothing on the table there. Okay, so nasty little asterisk on our theorem. So we have to ask, is this vector field, is that a gradient of anything? And yeah, sure it is. Look at that. Right there, x squared, y squared. You can confirm for yourself without too much trouble. Take the gradient of this function. get exactly F, and we win. How are we doing? Now, one thing I have not addressed here is, where did that come from? Did I just pull it out of a hat? Right? Did I just consult my inner oracle and my inner try x squared y squared? No, right? So there is a way, there's tricks for how to find the anti-gradient if it exists. And we'll talk about that later on. For the moment, I just want to get some wins under our belt here and talk about other related ideas. We'll talk about how to find anti-gradients. It'll end up being next time, not today. Anyway, we have an anti-gradient. Oh, missed. So that is our F into which we will be plugging. Right? And now keep in mind, I've got to plug in the start point and the end point. Okay, well, my start point I can infer from the fact that 0 is the starting value of t. Plug that into the curve. That gives you that point, and that's the starting point, which goes there. And then t ends at pi, which gives me that point as my end point. That goes there. And arithmetic, off you go. And it turns out that the value of the line integral, this integral I wanted to compute, is 0. What do you think? Everybody okay? Yes? Mm-hmm.
Does scoring theorem only apply for closed boundary?
Yes, Green's theorem only applies to closed curves, which are curves that are the boundary of something. That's right. Yeah. Yep. Yep. That's the big catch, the big asterisk, the limiting factor for Green's theorem. Yeah. Okay. All right, fundamental theorem alignment. Really powerful result, you'll notice. This integral, I didn't have to pull back through a parameterization. I didn't have to compute an integral. I just had to have a little bit of clarity on the magic function. I guess I had to take a couple of partial derivatives to confirm that it is what it's supposed to be, right? But once I've got that magic function, no calculus left. It's just plugging in. It's just arithmetic at that point. So the fundamental theorem of line integrals is super powerful trick. Okay, I'm going to set that aside for the moment. We're going to move on to we're going to come back to it in a few, but we're going to talk about a related idea called path independence. It's a little bit of a weird idea. It's a seemingly kind of implausible idea, but I claim it's not implausible. It's going to seem implausible. Here it is. Here's what the idea is. A vector field has this property called being path independent. If whenever you have two curves, like let's say I'm going to say C1 is a curve like that, and then I'm going to say C2 is a curve like this. Right? Now, so any two curves, now those two curves do have to share the same starting point and the same ending point, and that is a very important little detail to this concept. Same starting point, same ending point. A path-independent vector field is one where whenever that happens, the line integrals are equal to each other. And that is an outrageous suggestion if you really think about it. Don't worry about the rest of the curve. It doesn't matter. The mere fact that green and blue here share the same endpoints, and that's all you need to know. The green line integral, the blue line integral, that's all the same. How could that be? Doesn't that seem kind of nonsensical? Right? I think it's nonsensical. I mean, come on, it's got to matter that the blue curve did this kind of loop here. Doesn't that matter in some way? According to path independence, it doesn't matter. Now, I emphasize this is just a definition, right? Right now, it kind of feels like there should be almost no vector fields that satisfy this property. I guess technically the zero vector field. Yeah, sure, the trivial examples, right? But how could any other vector field have this property? Surely, as I compute the integral, as I move along this green curve, surely what the vector field is doing over here, which should be entirely disconnected from what the vector field is doing on the blue curve, the fact that we're evaluating the vector field in totally different locations. How could you expect that the value of the line integrals will always be equal? Seems highly implausible. Case in point, let's look at this example right here. And I'm basically at this point, I'm trying to, just for kind of dramatic purposes, I'm trying to talk you out of believing that there are path-independent vector fields, and then I'm going to show you that there are some. But here's my intuition anyway. I'm going to look at these 2 points here as my start and end points. We'll look at this green line integral, and then we'll look at this blue line integral. We're just going to kind of, eyeball and see what these line integrals ought to be. We'll start with the green one. The vector field is 0 along that left segment. The vector field is 0. There's no line integral. Along that top segment, the vector field is going up. The curve is going to the right. Those are right angles, so f dot dx is going to be 0. So there's no line integral across the top either. And so altogether then, that green path from the starting purple point to the ending purple point, on that green path, the line integral is 0. Yeah? Okay, let's look at the blue path now. Well, again, we have some orthogonality happening here. The vector field's up. The curve is to the right. That dot product is 0. So there's no vector field along the bottom. But look what happens over here. On that edge, the curve is going up. The vector field is up. The vector field is non-zero. There's a positive amount of line integral here. And so on the blue path, I guess I better link it up there. On that blue path, same starting point, same ending point, not 0. So clearly these integrals are different. Of course they're different. I was looking over here as opposed to looking over there. You look at different places, you get different values for the vector field. Everything should be different. Right? All right. Okay. So let me now try to persuade you that not only does there exist an actual path-independent vector field, but in fact there's bunches of them. And here's the argument. Let's fix a starting point, fix an ending point. All right, we're going to look at this green curve there versus this blue curve there. And let's think about if the vector field were a gradient. What would happen if our vector field were a gradient? Well, if it's a gradient, then I can compute this green line integral with the fundamental theorem of line integrals, because it's a line integral of a gradient, and line integral of a gradient is f of b minus f of a. Right? Fair? That's our fundamental theorem of line integrals that we just learned 20 minutes ago. And now let's look at the blue line integral. The blue line integral, well again, doing line integral of a gradient, so also f of b minus f of a. Fundamental theorem of line integrals, again, our new tool. And notice, because a and b are the same starting point and same ending point for both of these curves, and we're plugging in the same anti-gradient because we're using the same vector field, both of these integrals are equal to the same expression, and so they're equal to each other. Isn't that interesting? I think that's just wild how despite intuition suggesting that this is an insane pursuit to try to find a path-independent vector field. Get out of town, right? Here you go. There's a bunch of them. Any gradient, path-independent. How we doing? Is everybody happy? Okay. All right. So it turns out that this goes both ways. What we've shown here is that if you have a gradient then it follows that it's path independent. It turns out the arrow does go the other way if you have a vector field that's path independent, and there's regularity issues. This being Math 219, I don't want to get bogged down talking about continuity versus differentiability versus C1. We need to know what those things are, but it's not going to be our focus, right? But regularity issues aside, path independent vector fields are gradients also. So these are one and the same. But again, minus regularity nonsense. Okay. All right. So now here's another way to say path independent. This is going to be useful in a few minutes. Let's see here. Speaking of which, we have 5 minutes left. I just want to check time. Okay, I think we're doing all right. Okay, let me remind you what path independence says. Same starting point, same ending point. Value of the line integral along one curve equals value of the line integral along the other curve. Again, same starting point, same ending point. Now, if green is equal to blue, well, then I can do the arithmetic, subtract one over to the other side, and I get green minus blue is equal to 0. And I claim that green minus blue is in this picture over here. We just have to think through, okay, what does that look like? The green curve and then minus the blue curve. So we're going to move along the green curve, and then it says go backwards along the blue curve. So if you move along the green curve and then go backwards along the blue curve, notice you're just doing the loop. You're going from the starting point over to the ending point and then continuing on and then back to that same starting point. So, so specifically then, what I have in orange there is what you might call green minus blue. So, saying that green is equal to blue, another way to say that is that all closed line integrals are equal to 0. What do you think? Is everybody happy with that? It's a different way of saying the same thing. Okay. All right, I'm going to leave that. It's not hurting anything. Okay. All right. So just as an example, and I think this is largely for fun, but I don't know if you all are familiar with the artwork of M.C. Escher. So he did a lot of kind of brain bendery, kind of optical illusions in art kind of stuff, and it's all fun. So this one here, this piece of work here, I think I forget the exact name of it. I just call it the Escher stairs because the stairs are the point of this picture. And let's watch what happens to let's say this person right here. You can see he's going up the stairs. And then the people he's following behind, well, they turn right, and then they kind of keep going, and then they turn right again, and they keep going. And another right turn, and come right back to where they had been. So, wait a minute, how is that possible? How can you keep climbing up and up and up, and then come right back to where you had been? That's obviously nonsense. Right? Okay. All right. Well, so here's a kind of a math point of view on that. That is to notice that the way we keep track of how much altitude changes, right, is with, gradient. Right? That's how you keep track of how much altitude changes is by doing dot products with the gradient of the altitude function. Right? That's an old math, an old chapter 2 concept. Right? So, all right. Well, since it's a gradient, being a gradient means that it's path independent. Being path independent, as the formulation that we have up here, if it's path independent, then all closed line integrals are 0. And what this means is that the total amount of altitude change should be, in fact, 0. Right? Does that make sense to everybody? Okay. All right. So this is kind of pointing to the the nonsense of the picture here, right? The idea is that if you're going uphill, as you go all the way around, the integral, according to this picture, the integral's positive. The integral is, well, it's positive all the way along. I'm adding up positive gains in altitude the whole way. Of course it has to be zero because look, they're coming right back to where they had been. So it is a contradiction in that the seeming effect of doing the climb ought to be positive, but the actual effect of coming back to the same point is that the altitude change is zero. Does that make sense to everybody? So this is just kind of a mathematical take on what's contradictory about the Escher stairs. Okay. All right. Alrighty. Let's see here. I'm sorry, and then I ended up running out of time after all, so that that'll do it. We'll draw the line here. We will pick up here on Wednesday. I hope you all have a good early part of your week. See you on Wednesday. And don't forget to stick around.